All right, excellent. Thank you so much again for inviting me, Miriam. It's a great honor to be there, and it was really fun to just sense the energy in the room and sense what this new generation is up to that will hopefully bring us a new way of designing chips in much more efficient and much more inclusive and accessible ways. And this is pretty much what this presentation is about. I feel I may be preaching a little bit to the choir because you guys are actually living pretty much what I want to talk about, which is the democratization of IC design and the energy that I feel behind this new movement. So hopefully you find it encouraging that people like myself who are from a previous generation, I started IC design in the early 90s, are also excited about this. It's not just you. So this is a talk that I gave at the CICC, and it's shortened a little bit and updated. But mainly what I want to do is first zoom out a little bit and talk about software, because this is where open source really started. And then brainstorm a little bit what's different about hardware and what are we about to see in IC design specifically. And then lastly, I want to summarize what we've been doing within the IEEE SSCS. I'm actually continuously surprised that many people don't quite know what open source is, so it makes sense to talk about that just for a couple of minutes. A lot of people think open source just means free stuff or something, but it's actually a lot more than this, and it's important to understand what the main ideas are. So the idea of open source was kind of spelled out in the early 1980s, and roughly speaking, the open source paradigm means that you're creating something that's publicly accessible and it can be modified and reshared. This doesn't mean, again, that it's just free and it's sitting there. There is actually still a license attached to it, and there's different licenses available. Many of you are expert on this. There's an MIT license, a GNU license, Apache license, and so on. And these licenses, they spell out terms. For example, how can your code or whatever you're sharing be reused, and what are some of the implications of that reuse, and so on. But the main idea really is to foster open exchange, open collaboration, transparency, and meritocracy. So collaborate among diverse groups to yield better outcomes, allow multiple solutions to rise in parallel. So good competition, right, for solving a problem and vetting them in parallel. And there's also an interesting aspect of avoiding central points of failure. If suddenly your EDA vendor goes out of business today, well, you may not have a replacement immediately, whereas in open source, it's more like a community perhaps managing a piece of software, and hence it may always be up because different people can maintain it over time. So all of these ideas had extremely humble beginnings in the 80s. And then we started seeing projects like Linux. Okay, everyone knows how successful that is, but even that now is history, and we're actually looking at an extremely sophisticated ecosystem in the software world that is built on this open source idea. Just to give you an example, I'm using PowerPoint software here, and many of you may not be aware of it, but there's a huge amount of open source software utilized to create PowerPoint. You can actually open the license file of your PowerPoint, and you see here some initial license agreements and so on of Microsoft open source code. And then you go through this document. It's actually 222 pages long to give you a feel for how many packages are cited here. And at the end, you see some humble reference here to some zip tool or something that they license. So under the hood of PowerPoint is a humongous stack of open source code. Many people are not aware of this, and this essentially allows Microsoft to be a lot more agile. Another example is a Ruby on Rails web development framework. So if you are a company like Square or Groupon or Airbnb and you have your business idea, you don't hire a bunch of C programmers and write all sorts of code from scratch. No, you actually build on existing web development frameworks, and Ruby on Rails is one that's open source, and that basically enables these companies to innovate very quickly and focus on their idea rather than the low-level details. And again, these types of tools, they are shared between different companies that have entirely different business ideas, but can share the same kind of backbone. So this all sounds so brilliant. What's going on with open source hardware, or what is it even when we talk about open source hardware? Well, in open source hardware, instead of talking about code, I guess we could more generally call it design specifications of a physical object, how it's constructed, how it's supposed to be put together, and so on. And so the source code in this case could be schematics, blueprints, logic descriptions, drawings, and so on. And so what we all hope in this community of open source hardware is that there could be similar benefits that the software industry has already extracted: more design productivity, community review and improvement, education, tinkering, attracting new talent, and so on. So far in hardware, as you may be aware, it's still a paradigm with a very, very small footprint. And one exception is, for example, the guys at CERN who put out a bulletin here about this, who have essentially open sourced some of their board designs, and they're sharing designs, and they get input from the community about them. And so this is kind of an early stage push for open source hardware. A few years ago, people reviewed the overall state of this, and they made a nice table here that basically points out, to begin with, there are different abstraction levels in hardware that we can think about. The first is kind of consumer hardware, and here there are actually kind of system level ideas. For example, there's this Pebble watch, which is mostly open sourced, and you can write code for it. You can look at how the hardware is put together, and that may allow you to contribute to this hardware platform. There's also enterprise system hardware like the Open Compute project, designing interfaces and so on that then evolve into standards, and people can share specs to design for and so on. And then on the circuit board side, we all know tiny circuits and Arduino. This is more or less for hobbyists. But then back in 2016, actually, when you looked at semiconductors, our space, IP cores, design automation tools, and so on, it was actually still pretty empty. And this is a little bit of a shame, because when you go way back, even before my time, right, in the 70s and 80s, we used to be ahead. SPICE was actually created and open sourced, so to speak, before the term even existed. So SPICE was just put in the public domain, and everybody could see and use the code. And that was in the 70s. Larry Nagel and Don Peterson released this. And again, this was before anyone even coined the term open source. And then came Magic, and the situation was very similar. Extremely successful open source project that's actually still maintained by Tim Edwards and others. But somehow since then, it's been pretty quiet. And so you may ask, what's going on, and what's the difference, and what's the present state of the art, in particular when we come to chip design. So in a way, I guess the sad picture that we have evolved into on the hardware side is that everything is extremely vertical. So there is certainly IP at the bottom, and tools and so on that are shared by the different companies. But everyone has their own, typically from their own ground up design of IP blocks, even tool enhancements, often libraries within each company. And so this is highly siloed. Oftentimes this is viewed as kind of an opportunity for competitive advantage. But the point I want to make here is that as soon as you reach a complexity level that approaches that of a software product, you can actually make it work, as we just discussed, in the software space, where a common lower level software stack can be used to help multiple companies realize their business ideas without getting in the way of each other. And so really, in the long term, what I would like to see, and what I hope to see, what many hope to see, is that in the chip design, we manage to create similar abstractions and platform that can help these companies be a lot more productive in doing their business. And partly, I didn't say this explicitly, but we all know this. One of the grand challenges in the chip industry is manage complexity and manage design cost. So why don't we immediately do this and move on? And why don't we adopt everything that the software guys is doing? Well, the reason is there are actually pronounced differences between software and hardware. And here's a nice summary by Andreas Olofsson, who used to be a DARPA program manager. He now has his own startup. And it's important to point out that in software, you kind of have a different challenge when it comes to debugging versus writing code, reading code, cost of bugs, and so on. Just to point out the obvious, costs of bugs in software tend to be somewhat low. For example, if you have a bug in your Android software, you can just make a quick update. Often it happens automatically. You don't even know about it. However, if you have a bug in hardware, you may have to do a respin, and the cost of that is extremely high. It's not just the masks, it's really the time you have to spend with the engineers and in the lab to figure out what's even wrong with your design, improve it, tape it out again, and so on. So it's extremely costly. And so some of these, I'm not going to talk through all of them, some of these differences between software and hardware have made people extremely cautious. And so, as identified by DARPA, these are really the key reasons why hardware, and in particular chips, hasn't caught up yet. There's this high cost of failure. And then the next one is really a chicken and egg, limited capabilities in existing open IP. Well, that's something we can fix, and you guys are working on this. And then the other big one, and I think a lot of the stuff that you guys are working on in BAG and so on can help with this, is this whole verification challenge. So when you make a piece of hardware or design a piece of hardware, it's actually very difficult to prove without a doubt that this will actually work. So the sign-off tools and checks we have are just not as well developed as for software. And again, because the stakes are very high when it comes to the cost of bugs, this becomes an even more significant issue. So this is where a lot of the recent US programs started from, right? So there were these large DARPA IDEA and POSH programs that basically said, well, open source is great. We think it can solve a lot of problems in chip design, but we need new tools and abstractions. And so they funded a lot of people in academia and also industry to work on new tools such as OpenRoad, FASOC, Align. Some parts of BAG were also funded on this. I was also participating in this program. And really it boils down to making IC design a lot more programmatic. And I think this is what you folks are going to focus on in your boot camp. So the good news is that this is now kind of spilling over into more than an academic program. So Andreas, the former program manager of these programs, started his own startup called Silicon Compiler. It's an open source tool that essentially tries to get to a state of push button ASIC design. You got eFabless that basically looks at crowdsourcing. Essentially, if you have a company and you don't want to deal with getting your own tool licenses and hiring your own IC designers even, but you need a chip for your product, and even let it be a simple IoT chip or something, perhaps through a program like the ones that eFabless is doing or ChipFlow, you can get going in this direction. So this is getting extremely interesting, and alliances are being formed. So the CHIPS Alliance grew out of the Linux Foundation, and a lot of people are curious now about this momentum. So here you see a lot of companies, in addition to the ones we talked about now, like eFabless, you also see FutureWay and Alibaba and Intel and some large company who are just curious about, where will this go and what should we do next? And places like the CHIPS Alliance are a committee where you can discuss this openly and find some connections. Also worth mentioning, and many of you see this in the news right now, there's a lot of geopolitical tension right now. And this article from The Economist was basically saying how this may be pushing us toward open source, no matter what, to resolve some of these issues. So in summary, right from this introduction, I think there's actually no question that the future will be extremely interesting and exciting when we think about how open source may change hardware and IC design. But just to get down to the ground again, I don't think this will change extremely rapidly. We're very early in the game, and keep in mind that software took about 20 years or so to really go where it wants to be. So we need patience and we need a lot of energy, and we need some people, and the people in the room are best suited for this, to drive radical change and disruption. And I'm saying this because I'm observing that many industry players intrinsically will not be motivated to push for this. They have their own agendas. They have secret sauce that they will never change. They never started out with an open source business model in mind, and so on. So new companies will emerge and drive this. And we're seeing the very beginning of this. And I'm sure some of you will start their own companies, and I really look forward to this. But another aspect that I want to talk about is actually that this open source and new automated way of designing really requires new talents. My generation was brought up to design in a very manual way. Even digital design was quite manual when I learned it. And we need basically new players that come in and drive this. The unfortunate thing is that these are in short supply. Everyone wants to go into machine learning and blockchain and some other exciting applications. And chip design looks quite pedestrian to most people for reasons of actually not understanding what's going on. So what we really need to do is put a foot forward in competing for new talent. And open source is actually a perfect coincidence here, because it lets us access an opportunity, a community that was previously locked out of IC design. So, even 10 years ago, it would have been very hard for somebody to get their hands on the right tools and PDKs and so on to make their own chip and tape it out. But this has become a lot easier, and we can make our space look a lot more than other exciting fields like robotics, where you can immediately get going and you download code and you can share and you can join hackathons. It's extremely exciting. The IC design world that I grew up in with was, you're in a dark room under NDA and you can't talk to anybody. So no wonder nobody wants to do this, right? It's been horrible. And so this new movement towards open source really addresses this issue. So really what I'm saying here in summary is that this open source framework is really hitting two birds with one stone. So first, we get new talents because we can make this a lot more exciting and accessible. And second, we can start building a new ecosystem. And again, I think you guys' generation will be the leaders driving this change and really driving us to a point where we can parallel the success of the software community. So, right, this is all good, and really the main issue that had to be resolved, and this is a nice chart from Mohammed, was the PDK issue, because this was usually only available previously by signing NDAs. But luckily, we got this solved with the help of Google, who pushed and invested money and talked Skywater into releasing the 130 nanometer PDK a little bit less than 2 years ago. So this was at the end of 2020. So to me, this was one of these really big bang events, and I think all of you guys know about it. There was immediate success in terms of attracting people to submit designs to MPWs funded by Google, and we saw a lot of first-time designers on these runs actually coming more from the software space, kind of figuring out how to design simple processors and so on. But from here, things have grown substantially, and we're now past the 5th MPW. You see another exciting aspect of this. It's a very international crowd that gets together. that can talk about these tape outs, that can work together and leverage and improve. I think this is the main focus going forward, these existing open source design tools and flows, so that we can all be productive and really leverage this new technology to the max. So the community is growing very quickly. You must have seen these charts somewhere. When you go to the Slack channel today, it's actually over 3,000. So it's really growing quite rapidly. So meanwhile, I was sitting in some of these IEEE committees, and as early as 2020, I started thinking and brainstorming with people about, what should be next? What is really needed to go in new directions with solid state circuits, and how can we become a little more agile and connect to new trends within these kinds of IEEE organizations. So we looked around, and this open source development was basically the first thing that caught my eye. So I suggested that we embrace this and we organize a workshop. So in April, we had a workshop that had some of the highest attendance of events that we ever had. And we had Tim Ansel and others speak at this event from Google. And people immediately became excited about this within solid states. And so that really led us to do something that we've never done before, which is set aside some money to actually fund silicon tape outs. And so we call this the PICO program, Platform for IC Design Outreach. So we sponsored some fab runs and are continuing to sponsor some fab runs. And we're doing this through a contest. And the idea really is to get people excited about ICs and help build this new community that I've been talking about in the previous slides. So there's a program website where you can go, where everything is kind of summarized. But really the basic idea is to say, okay, we're going to hop on these same runs that Google is supporting more or less, but the paid version of it, Chip Ignite programs through eFabless. And in 2021, we bought a number of these slots. We gave out 4 of them to a team of undergrads by Purdue. Then we targeted some countries that didn't have easy access for tape out to provide them an opportunity. And then we had 6 slots where we said, let's do a contest and battle it out. And this is really what we call the SSC PICO Design Contest, or Chipathon as we call it now. And this was wildly successful. I did not imagine that it would be this successful. We got a lot of good proposals in 2021. 18 teams were selected and 11 actually managed to tape out at the end. We gave them a free IEEE memberships. There is actually a new student chapter evolving in Pakistan on this. And so you see there was international participation. We still have some work to do. In Europe, I guess everyone was on vacation when we did this. We also want to get some more footprint in Africa, but this was a very, very good start for us. And here's a Zoom window from our weekly meetups. Sometimes you get up to 100 people show up there and ask questions about tools and IC design. And it's been extremely fun. This is some of the most fun I've had in IC design since I started my career. Here's a quick look at what was taped out. So one of the new aspects really, and this is what I find fascinating, is that you can now combine things, right? So here you have a chip with a processor from the United States, and then a band gap from Egypt sits in the corner here. From 2 entirely different labs, there's no agreement, nothing. The files are just shared via GitHub and taped out together. This is fascinating. So the designs that we were able to tape out here are relatively basic. Of course, we're not really pushing the envelope in terms of, getting silicon to physical limits, but this is really important for people to get a first tape out, build experience and so on. That's more or less the spirit of this. And obviously all of this is shared on GitHub. This is really the open source spirit that we're pushing also through this program. There's a few very good outcomes here. I want to share one here from the University of Missouri. There was a graduate student who led some undergrads who had never even seen ICs before. They wrote some Verilog. They had an idea of building a sleep apnea machine learning processor, and they implemented it in Verilog, and they ended up taping it out. And this student gave a very nice testimonial. I'll skip her video, but basically we managed exactly what we wanted to do, get new people in this space and just learn about the possibilities of chip design. So with all this momentum, right, we're going to grow this also within the IEEE. 2021 was an experiment, and I showed some success, and I went to our leadership and said, okay, this really requires an entire committee to work on. We need to expand, we need to feed this contest with new ideas, we need to grow, we need to advertise, and so on. So I formed a committee that's called Technical Committee in Open Source Ecosystem. You may realize some people here, Mirjana is on it, and some other folks you may know. So this is a pretty diverse group of people from all the different continents, kind of trying to figure out what we should do within the IEEE. And if any of you have ideas on how we could help promote open source in any way, please approach me or anyone from this committee. We're super excited to make anything happen that makes sense for the community. So the first thing we did, of course, is organize a new chipathon, and so that's been underway. It started on May 1st by collecting proposals. We then again picked teams, 22 of them, and again, we're holding these meetups, often attended by up to 100 people or so. If you want to join these, you're happy to do so. I'm actually always looking for people to present. If you want to show your tool or your insights, this is a good topic for these meetups. They're kind of happening since June, and they will go until November. And so again, you see we have reasonably good international participation. I'm happy that we also have a team from Austria now. And so on. We still need to work on Africa, and Asia is also something we need. I definitely need you folks from Korea to help us advertise this program and get some teams from Korea into it next week. So yeah, beyond this, beyond the chipathon, the TCOSE is talking to entities like Chips Alliance to see what should be done and how the IEEE can contribute. We want to interact with IEEE chapters. If you're in a chapter and you look for a speaker, perhaps someone from our committee can speak. We also want, and this is another very important topic that is of interest to you guys, we want to push for venues where you can publish open source papers. Because right now it's pretty difficult. You run a nice open source project, where do you go? There's the Free Silicon Conference, but beyond this, there isn't a whole lot. So we are the committee that will push now inside the IEEE to make sure that all the top-notch conferences will have sessions for open source dissemination and so on. We also have a little website, and again, if you have some ideas on what we can add here, that's basically meant people to help get started. Basically, if you know nothing, you can go to the site and say, okay, here you can download the PDK, and here are some containers, and so on. So with all of this said, I hope I clearly conveyed that I'm strongly supportive and that I sense all this energy. It's really important to realize again that we're only at the beginning. So here's a roadmap from the Chips Alliance that basically shows some of the beginning and things that are evolving at the front of IP and reusable SoCs and cores. And process technology is really an area where I think we will see a lot of new developments coming up. In this roadmap, it was speculated there would be new open source PDKs, and we've actually seen some announcements recently. We're very close to having another open source PDK from Global Foundries for 180 nanometers. So I think this is already available in experimental form, some alpha version, but it's only a matter of time, it seems, until this gets released for production. And then some of you may have seen the news that Skywater is going to release their 90 nanometer process as well, and they got some government funding for this, which is excellent. The general climate in the US right now is that people are realizing that there's a huge shortage in the workforce, and so the government's willing to fund these types of initiatives. So this is something that is probably 6 to 9 months away when you can actually download this PDK and start taping out with it. And so 90 nanometer really gets us to a point where you can do pretty high performance chips. And I find that extremely exciting. So in summary, really, I realized that I'm preaching to the choir here, but I was hoping to review on how this new open source paradigm is a vital ingredient of today's software ecosystem, and how our industry or community is exploring similar ideas to get into the same kind of shape. So this starts with low-hanging fruits on the industry side, design services, instruction sets, I/O cells, and so on. Some startups going in this direction. And we will see, the jury is out, how much traction this will gain and what the business models will look like. So people will definitely have to think about this. How do you make money with open source IC design? How do you make essentially money at the abstraction level above the level where you use these tools and reuse other people's ideas? Software has completely figured this out, but in hardware, it's only a matter of complexity until you get there. And this is why I'm very positive that in 2 decades, we won't even be questioning this anymore. Independently, and I think this is today, open source is an immense game changer for education, getting new talents on board, getting new talents excited, getting new talents actively think about new ideas on really what this community should be doing, getting together, having fun, doing hackathons, making IC design a lot more fun than it was when I started it. So this new fun factor is something I hope you guys feel, and something we can hopefully chat about some more here in this forum. So thanks everyone for listening. This is really all I had. Thanks for attending.
Okay, great. Thanks, Boris. Tell us, how much time do you still have for some questions? I'm sure that you're busy.
15-30 minutes is good. Yeah.
Okay, great. So I will ask the audience, on the site, let's say at Silicon Ocean Labs or online, if they have some questions for Boris, please, state your name and your question. Thank you.
We need an icebreaker.
Okay, I have one question regarding your proposal for any open ideas in the website. You said if we need to add, what do you mean by new open ideas? Some development in the software, the back design itself, or different options to make it simple layout or faster checks?
Can you repeat the first part of your question? I didn't quite hear that.
Regarding our new point or new update for the website you already shared, if we have any new ideas, so we can show with other. So what do you mean by these ideas? Software programming or update in the back design itself, Python scripting, or adding some new feature from the design itself?
Oh, mainly what this website is for, the one I showed for TCOSE, is pointers to resources, right? So let's say you developed a new tool that you want to share. Perhaps we can add a link there, right? And so you could let us know. Because a lot of people will hopefully go to this site in the future. It's supposed to be a central point. So something along these lines, right? Yeah.
Okay, thanks.
Or if you have a nice repository, right, that has interesting IP, there we can collect some of the links. But yeah, it will evolve, but anything goes pretty much.
Okay, perfect. Thanks.
Anybody else from the audience? Oh, sorry, please.
Yes, do you hear me, right? Yeah.
Yes, Jorge, please go ahead.
This is Jorge Marin from AC3E here in Valparaiso, Chile. Some of our students are there in the bootcamp, so we're really happy about this. Thanks a lot, Boris, for the presentation. Even if, yes, you say you're preaching to the choir, I think after this we're even more convinced that this is a very good way, even more for us that we're a bit far from the center where these things are happening. So my question, I actually have many questions, but regarding being far away of the centers where this knowledge is being used and is connected with industry. Do you have any ideas of which strategies in general we should try to focus on for getting this into a more, yeah, as you say, like industrial or applied form, these open source ideas for hardware? I don't know if I'm explaining myself.
Yeah. So you want to create something that has real world impact, or is that what you mean? Or
yeah. For example, doing a chip that will actually work. We have yeah. Well, yeah, that's, I know that's hard even with industrial tools, but for example, here we have a lot of interesting problems in Chile. We have, well, the mining industry, we have agriculture industry, and we would like to apply these things to these kind of problems. But the eternal question is how to start, where to start from. I mean, we are starting already, but how to, yeah, I don't know. I don't know if.
Yeah, this is actually an interesting discussion topic, and maybe many other people can chime in here. This is something that I'm grappling with all the time. It is definitely, you know, someone said this at a conference recently again, to be good in an advanced field and really do things that work and have meaningful contribution and so on, it seems like you have to invest about 10,000 hours, right, of training. I think this is true for many fields. This is also in athletics, I guess, right, to be a high-performing athlete or something like this. And it seems to be still true in IC design. So I think really to make a chip that has a real-world impact and that you can maybe use as a sensor in mining or, you know, whatever, you need a lot of experience. And I think, I mean, my personal opinion is that perhaps we shouldn't mix education with necessarily solving these kinds of problems. I mean, not in the sense that we shouldn't use them as targets. I think it's totally fine to get students engaged in chips that solve real-world problems, but really making them work, right, and yield and be robust and programmable and cheap and all these things. I think this is something that industry has to do. Most of what you can hope for, in my opinion, as a student is to be inspired by a real-world problem, learn the fundamentals, make some mistakes that you will then never repeat again, right, when it really matters. I think this is a lot of what academia is about. This is the time when you can make all these mistakes. And sometimes people say, you know, really the amount of experience we have is really measured by the number of mistakes you've made. And really, as a student, this is your time, right, to make mistakes. And this open source business allows you to make them quickly and to share your ideas and your mistakes with others. So this is one way to think about it, right? But yeah, I mean, you're asking a very valid question, but I think my personal opinion is maybe we shouldn't get ahead of ourselves. I think we should focus on really educating people, making sure this is all fun. I personally, I don't see a route, right, kind of from 0 to 100 real quickly where you can make something that runs in the real world. And I think this has to do with the nature of hardware. In software, I guess any high school student can write an app that overnight becomes a worldwide success. I currently don't see a route for this in chip design, to be honest with you.
No, very interesting. Thanks a lot.
Yeah.
Also, short other question. Yeah, of course, we're responsible of educating our students, yeah, training our students in these things, these topics. Very exciting, of course. But yeah, this responsibility also is connected on how they will integrate in their professional lives. Again, since we're far from the centers where these developments are being done, how do you see this other topic?
Yeah, I mean, one thing to say is I think open source actually enables you guys to be closer than you may think, right? I think, yeah, in a world of NDAs and commercial tools and so on, I think you folks may have been further away than you are now. And I think there's huge opportunities now, I think, in your region to actually start some of these new companies, right? Kind of the IC design company 2.0 that builds on open source and crowdsourcing and so on. And hopefully, you know, this could lead to an avalanche where really, right, the new place where these things are done is actually not in the traditional places. I could very easily see this happening because some of the incumbents are just not incentivized, right, to go in this direction. And so the new players with the fresh ideas, they may be in completely different places. So I think it's actually a great opportunity that you guys have, and you certainly have talents, right? So I think it's a fantastic opportunity. I would look at it as the glass being half full rather than half empty. I don't know if that answers your question, but
very, very, very insightful. Thanks a lot, Boris.
Yeah.
Anybody else would like to ask Boris a question? We still have some time left. Ryan? Who wants to? Okay.
Hi, Boris. Thank you for the talk. Quick question. What is your, would you comment on what industries would think about this open source? You mentioned a while ago that you can reduce costs because of the design and all that, but sometimes like some industries really require you to use non-open source tools like Cadence or Synopsys. So in school, yes, I agree with you that it's open source tools are the best way to go because at least students can access it locally in their computers without having to remote. But then when they graduate and move into the industry, usually industries require these special tools instead of the open source. So any thoughts on that?
Yeah, and you know, this won't go away, right? These tools will be around. I think the best way to think about it is that these two tool sets, like the commercial one and the open source one, they will always coexist. I don't think open source will ever displace the commercial tool side. And I guess you know, Tim Ansel talks about this a lot, where he says even in software these things coexist, right? So you have a lot of open source tools for which there are commercial equivalents, right, that you can buy, and it really depends on which one you prefer or what the features are and so on. And so open source in a way could be for training and mainly for training. But I think maybe we should differentiate a little bit. Really going forward, what I see the open source tool side to be good at is more of an inspiration for the commercial side. So some of the things that you guys are working on, right, like Lego or Bag or things like that, well, there isn't really a commercial equivalent yet. So in a way, the open source side is actually ahead. But I have no doubt in my mind that some of these commercial tools will also advance. And so for this generation of new students who are getting educated now, who have fresh ideas, it's actually fantastic, right, to have an ecosystem where you can think outside the box of Cadence. And I think this is actually extremely important, right? Because if we just limit ourselves to the capabilities of Cadence or Synopsys or Mentor or whatever these tools, well, we will never make much progress, right? I think it's a very important role of open source to think outside the box. There's another aspect I want to throw into this piece of question. You know, when you look at a lot of people from my generation, I see this all the time when I go out and consult for industry companies. Many designers, especially analog designers, they're very reluctant to spend time on coding. They view their most productive use is to click around with the mouse on schematics or calculators or something like this. And in my opinion, this is really an outdated way of designing. We should be scripting, we should be capturing design intent. Right? We should be automating a lot more. This is how you manage complexity in this field. And as the complexity grows, we simply don't have time anymore to do all this manual clicking and so on going forward. But it takes time for a new generation now to bring this new spirit of really a fully scripted design flow and automated design flow to the industry. So again, if all you had was a Cadence environment or a Synopsys environment, it could be quite limiting. I understand that many things can be done within these frameworks as well. But I think open source is great to just break out of these barriers and do something new, and at the same time, right, educate the mindsets that will drive this and ultimately implement it in the commercial tools. Some of you guys may actually join Synopsys or Cadence, and you will be, you know, the whatever VP of R&D that implements this in the, 2027 version of Cadence. So I look forward to this. So again, I think the two will always coexist, and I think it's actually very healthy to have that.
Okay, any more questions coming from the audience? Okay, Achilles.
Well, hi, Boris. I think that it's very nice that we're developing tools that allow us to design hardware and in a agnostic manner, PDK and all that stuff. But when we talk about printing these circuits, I think that may be a kind of bottleneck, because with Sky 130 depends on the Skywater Foundry, right?
Right.
So I was thinking about what if, I don't know, a country or a university can design or implement a laboratory when they can fabric the integrated circuits. I don't know if that's possible with, I don't know if there are a kind of maybe implementation secret, I don't know.
Well, yeah, this is a great question. I mean, implementation secret, I should say, there's definitely secret sauce, right? When people make the next, 3 nanometer transistor, 5 nanometer, 7. In the latest node, you always have some kind of level of secret on how exactly you do something. But when you speak about 130, 90 nanometer, I think most of the secrets are out. I mean, to me, 180 nanometer is almost like PCB design. There's really not much of a secret sauce. Many people know exactly how to run the machines, what the recipes are. It just boils down to money. So you have to go and talk to Applied Materials and some of these other vendors and get the machines, buy the machines, run them. And one of the issues is, there's a huge, first of all, there's a huge initial capital investments, right, to have a fab. And then there's a lot of investment needed to keep it running. So you have a huge electricity bill, right? And you need to buy all the supplies and all these things. So you actually have to have revenue, right? And so Skywater has revenue, right? They have actually customers. They don't just do open source tape outs and things like that, where they get paid a little bit of money for MPWs. They actually do volume production there as well. And this is how they amortize the fab. So for a university to do the same thing, that would be very difficult. I guess the closest you may get to something like you're describing is probably experimental fabs like the one that Leti has, CEA Leti in France. They have a pretty good prototyping fab that can probably easily make the kinds of chips that we're talking about, maybe even below 90 nanometers and so on. But they are also very strongly funded by the government, and they have huge expenses, right? So yeah, for a university to come along and do something like this, I think that's probably not feasible. At Stanford, we used to run a 2-micron CMOS process in the 1990s or something like this. And it was very bad. It had only 1 or 2 metal layers, maybe just 1. It took a very long time, and it was still relatively expensive. So I think it's a little bit like on the software side. I think for fabrication, we need some synergy between the commercial side and the open source / education side. We kind of have to ride on the elephant's back a little bit, right, with this open source stuff. I personally don't see a route on how we can change this unless the government really kicks in a lot more money, and then we would be talking billions, right, to make something like this happen for open source only and for us only, right, for universities.
So the limitation is about the investment, but not
Yes.
about anything related to licenses.
I don't think so. No, it's yeah.
So everything it's open source.
Well, I mean, again, if you talk about 3 nanometer, 2 nanometer process technology, there's secrets there. But I think even for 90, many people could do this out of the box. You just have to buy the right machines.
I'm talking about the Skywater PDKs. Skywater 110.
Yeah. I mean, if you talk about 130, 90, I don't think there is much secret sauce there.
Yeah. Thanks.
Yeah. So if you have some money, yeah. just buy the machines.
Okay. Anybody else? Okay.
Yeah, I have a quick question. Hi, my name's Curtis Mayberry. I'm from Skyworks. Let's see. So, do you have any suggestions on how to kind of? Is there a good way to, I don't know, transition traditional designers to these new methodologies? Right. I mean, yeah.
Yeah.
Is there, and kind of corollary to that, kind of being right, we have these existing design flows that are using those commercial tools. Is there a good way to start introducing some of these open source tools and frameworks and getting them to to some extent work together?
Yeah, I think I mean, maybe Mirjana has a good question on this. I think some of the low-hanging fruits could be there are definitely companies out there evaluating BAG, tools like BAG, right? Where you could make a case that, if we actually capture design intent and write some code that give us some generators, right, we would have much better reuse within our company. You could make a case for that, and that could sometimes motivate designers to get on this track. In my experience, and it would be really interesting to hear what Mirjana has to say about this, is the kinds of designers we often see in existing companies, they're not interested in coding. Because, once you use tools like BAG or any other tools that come out of open source that are more in the direction of automation, you're coding a lot more rather than just, clicking on buttons and looking at SPICE waveforms and things like that. And I think this is a barrier. Now, the new generation, the people who are sitting in the room, they have no problem with this. They grew up like this, it's great for them. But people my age, they sit there, if I wanted to be a programmer, I would actually work at Google. I don't want to do this, right? And this is often what I keep hearing. But once you say that, next time you can actually do your design much faster or something like this, this could be a nice little carrot.
Yeah.
I don't know, what do you think, Mirjana? I think you've been trying to advance this within industry, right? More than me.
Well, we are not, let's say, Silicon Ocean Labs, not exactly an industry. And yeah, I might even make it here official from 1st of October. I'm joining Infineon in Villach. So, and they are going pretty strong into this direction, pretty ambitious with the Anagen program. So I believe for like to solve this problem, I will propose the mentoring or let's say a legacy program where you bind together a new, let's say, master student with a very experienced engineer who is like in the next 5 to 7 years going to retire, such that, you know, this experienced engineer, his knowledge is basically transferred to this new person or two, and to the script. Because, you know, whoever is close to retire, it's very and it's kind of ungrateful to ask for people to change the way they have been doing things forever. I mean, and also, you know, they say habit is a success, which means, which brings them there to be so successful. You know, we're asking them to change that before they retire, which is difficult. And also the target group, you know, for this new methodology needs to be, you know, like, let's say, a different age group. But I will probably say a bit about it during the ESTERC talk that I should be preparing. And it's happening in September.
Yeah.
So,
yeah.
but we can discuss about it maybe later on. I have one question for Boris, but I would like others to ask. If not, maybe I can use my chance. Okay, Kevin, please.
Thank you, Boris, for the presentation. I'm Kevin, and I have a question. Do you think that the open source tools can be an inspiration to next generation of academics, and how can it impact?
Can you repeat? Somehow the audio wasn't so great.
Okay. Do you think that the open source tools can be an inspiration to the next generation of academics?
Okay, you mean if you want to become a professor, or?
Yeah, make papers and articles, something like that. Yeah,
absolutely. I mean, if you look out there right now, there's actually a growing community working on not just open source EDA in isolation, but kind of machine learning and algorithms, right, surrounding this. It's actually a wide open problem, right, to automate some of these with clever new algorithms and how to manage training these types of algorithms. I mean, a lot of these problems are entirely unsolved and are intellectually very rich, right? So I actually think, yes, this is a very good direction for academics, and I think you see some very good examples. Now, in terms of funding, of course, I think there's some catching up to do, because I think this area is not receiving enough funding just yet. And but I think this will change as we go further. I think this design bottleneck in chips is only growing, right? So complexity of chips is getting larger and larger, and we just we have our backs against the wall, right? We need solutions to make this much more efficient. And so, yes, I definitely would say yes, is the answer to your question.
I really think that the events or instance like Chipathon will help you to that.
Well, the Chipathon is basically for people to get the foot in the door. We want more people to understand ICs, get a feeling for how fun it is to design, how to work in this space, make silicon accessible. It's a very small contribution we're making through this Chipathon. And really what we're hoping, I guess what I'm hoping, is that other people will follow to make this much bigger, to make this, there should be a collection of Chipathons, right? There should be more than just one. We should all unite and come together and work together in ICs, very much like you see it in machine learning and robotics and other communities where everything is shared and open, and these communities thrive. And so I want to get to that point. Again, we're just at the beginning, in my opinion.
Yeah, thank you.
Hello. Hi, Boris. Thanks for the talk. So you said earlier that you guys were pitching for an open source design section for some of these larger conferences in IC design, right? So as of right now, do you think that does this mean that you think the current review process for these conferences may be, say, if someone submits a design with using Skywater 130 or 180, since these nodes are much older, do you think that uh, the the value of these designs are less in the eyes of the reviewers than, say, if it was a non-open source, if it was made on non-open source, more advanced nodes?
Yeah. Yeah, I mean, this is exactly the problem that needs to be addressed for these papers to appear. So, I mean, what it takes essentially is to acknowledge the fact that the art of designing a chip in a new and systematic way with new kinds of tools is an intellectual contribution, right? So when you think about why does your paper get accepted to a conference, there has to be some kind of a contribution that is interesting from an intellectual standpoint. You're proving something for the first time, you're advancing a certain specification or something. In the case of this open source business, it could be more of a methodology, a way to do things. You have a new generator to design something, right? And you're showing that at a conference. And by the way, we have already seen examples of this. There are some papers from the BAG team, right, where they showed successive approximation ADCs or something like this at conferences like CICC. And so we are starting to see papers like this, kind of one here, one there, getting sprinkled into these conferences. But we ultimately want to make sure that this becomes a little more systematic and is evaluated in a systematic way. And so we need to get people onto these conference committees and form subcommittees who actually understand these types of contributions and who can evaluate them properly. Because many of the existing program committees, for them, they don't even know what all this stuff is, and they can't evaluate these papers, right? So yeah, that change will take some time. And for the time being, there's a lot of workshops and things like that at conferences and isolated papers and sessions. But we really want to change this, and we're discussing with the society and the publications committee on what we can actually do to advance this. So this is all in the making. I think it's a totally solvable problem, because especially industry, I think, is interested in learning about design productivity types of things at IC design conferences, not just at EDA conferences. So yeah, I think this is coming. We just need to be a little more patient.
Okay.
Yeah.
I also have another question. So the talk, you were mostly speaking about the hardware design, trying to catch up with open source hardware design, which is a way to catch up with how big software is right now because of the community of developers that contribute to open source software, right? So there is also another gap in hardware, which is that automated analog design is quite far behind the digital design process. So what do you think is the biggest hurdle for automating analog design in terms of your design specifications and trying to generate that automatically?
Yeah, that's a really good question. I think it can be answered. I mean, I could talk about this for hours. I actually think that when it comes to analog automation, the first problem we need to solve is layout. Because I think this is actually the lower hanging fruit among everything is layout. I think we will eventually crack that problem with better algorithms and so on. When it comes to the actual circuit design process, I actually do not yet see how you can automate the creativity that a human brings to this space. And maybe I sound a little bit old-fashioned here, but I'm basically going back over 30 years, right? I mean, people have been trying to automate these things for 30 years. And the people who know these things really well, like Rob Rutenbar and so on, who, again, been working on this for 30 plus years, they will tell you one very important insight that I want to share with you. And that is, the design problem is actually not the way it's usually shown in papers. Design does not work as follows. It's not that you can write down all the specifications. Oh, I want this gain bandwidth product and this and that. Then you have a magical tool that somehow sizes a circuit or comes up with a topology or refines a topology. Design does not work like this at all. I mean, all of this is entirely wrong. Design is actually mostly about discovering the specification and constraints along the way. And this is why it hasn't been automated. So when you actually follow an experienced designer, obviously they start with some ideas of what the circuit can do. Oh, I need to, find the specs for a 5 gigahertz transceiver or something. I have some rough ideas. Something is in the standard. I have to meet a certain spectral mask and so on. But when they design the circuit, they actually come up with dozens of other constraints that are not defined a priori, but they discover that while inspecting the circuit, while simulating the circuit, and then they feed that back into the design process. This is the hard part. And how to automate that really beats me. I have no idea. So when you read all these papers, I always chuckle when I read these EDA papers. They say, oh, here are all the specs and constraints. They're all done. I can write them a priori, right, without even looking at any circuits. That's completely wrong. People are missing the main problem. The main problem is actually the discovery of the actual constraints and specs while you're designing this thing. You look at your SPICE window and like, what the heck is this thing doing? Oh, I forgot to specify, that common mode matters or that this matters. So now let me go back, and now my constraints changing and my architecture is changing because of what I just saw in the simulation. And people are missing this 100%, and I wish they would start to wake up. And so if you can offer a solution to that problem, you'll be a billionaire. But if you continue to work on problems where, okay, you have this gain bandwidth product and this load capacitance, here's my op-amp generator, it's entirely useless. That doesn't solve any existing problems. I can design such an op-amp anyway in 5 minutes by myself. But the real design is actually about discovering the actual constraints and the physics of the problem as you're going through the design iterations.
Okay, can I?
So that problem I think will not be solved before I retire. Layout automation will be solved before I retire. So I would work on that. Yeah.
So I know that we overstretched our boundaries, Boris, and I know that you have very close, like very soon, and the next meeting. So just like a question to kind of like as a follow-up of what you just saying. So my question is the following: could programmatic IC design approach contribute? I don't like you said, it is something, let's say, I believe programmatic IC design approaches, it should be something between EDA and the way we design things. So even if we kind of provide the skeleton, the people should pick it up and try to kind of follow up and develop the generators according to the specs. So my question is the following: do you think that it's possible with this approach to design faster and discover, along the way, the constraints that, that you have been talking about? So what I'm saying is, by changing the methodology, we will still have to face the same obstacles, and solve the same problems. But would it be possible that with this approach, we document it, we educate people, and by that, we speed up in general? Thanks.
Right. Yeah, I'm very optimistic about this. And I think this is exactly what we want, right? We want to capture intent and we want to capture discovery, right? So something you have already discovered and experienced and optimized, that should be somehow documented and written up in a way so that you don't have to go through that same thing again the next time around. And I think this is precisely what you're trying to do. But what it doesn't cut out, and I think you're already alluding to that more or less, what it doesn't cut out is that, yeah, once you go to a new process, to a new geometry, a new supply voltage, and you change the topology or something like this, you will make new discovery that changes your specs, it changes your constraints, and it'll do that continuously. But as you do that, I guess it boils down more to updating your scripts, right? And again, I fully agree that it's a great productivity aid not to start from zero every time you do something new, especially when it's about porting maybe just to an adjacent node, as opposed to 3-4 nodes down, which basically I'm not sure if you can learn anything from your design from 3-4 technology generations ago, but for adjacent design, porting, and for deriving similar architectures, I think this is the way to go. And I think the one problem that I see very pronounced in companies, I mean, especially in the US, there's a lot of throughput among IC designers. You join a company, you design something, you go to another company, design something else. Nothing is really documented to a point where people actually trust the schematics. If all you have is the schematics and you don't see the intent of the designer, of what were they actually trying to do, you will not trust this design. And this goes a little bit back to what I said earlier and what DARPA also recognized, that this is actually part of the verification process and the productivity boost is to kind of establish a way to create trustworthy designs. And when you give me a piece of code that tells me how you designed this and what your constraints were, at least I can look at that. When I look at a schematic that someone put together 3 years ago, I typically look at that set and said, well, I don't trust this thing at all. I don't even know what this guy was doing. So yeah, we definitely need to go in this direction. I have no question.
Okay, thank you so much. I believe we kind of already, step over the time that was given. But thank you so much for your goodwill actually to extend it. Your day just started quite early because of us. So I'm really grateful for your time and your contribution to our society, either like open source or not open source. We are definitely grateful to have you in both these fronts.